Now example 1. So find the singular points to the following ODE and say whether they are regular, singular, or irregular singular points. Okay, so let's 2x squared minus x cubed y double prime minus 5x y prime plus 3 plus x y equal to 0. So to do this, I have to find P and Q. So this is y double prime minus 5x over x squared times 2 minus x y prime plus 3 plus x over 2x squared minus x cubed, which is x squared, sorry, over 2 minus x. Let's erase. Minus x y equal to 0. So y second minus 5 x 2 minus x y prime plus 3 plus x over x squared times 2 minus x y equal to 0. So p of x equal minus 5 over x times 2 minus x, and q of x equal 3 plus x over x squared times 2 minus x. So you see the singular points are what? Singular points are whenever p and q are not analytic, these are rational functions, so it's easy to find them. X equals 0 and x equal to 2. These are the singular point. Now I have to see if it's a regular singular point or an irregular singular point. So for x equal to 0, x minus x0, which means x minus 0, xp of x is equal minus 5 over 2 minus x. Is this analytic at x equals 0? Yes, analytic at x equals 0. What about x squared q of x? This is 3 plus x over 2 minus x. This is also analytic at x equal to 0. And this implies that x equals 0. So first we should check if it's a singular point. Next we should check these two things. Is a regular singular point. What about x equal 2? So x minus 2 p of x, if you multiply by x minus 2, you get this is minus 5 over x. In fact, it's plus 5 over x. And this is now analytic at x equal 2. What about x minus 2 squared q of x? This is 3 plus x over x squared times 2 plus times x minus, so I'm multiplying by x minus 2 times 2 minus x. Sorry, times x minus 2 minus x, yes. And now this is analytic at x equal 2. Then x equal 2 is a regular singular point because these two are analytic. Now let's do a more interesting example, a bit harder maybe. So same question, example, same question with x times x squared minus 9 y double prime plus 2 times x minus 3 y prime plus, here I need a square, plus sine x y equal to 0. No, this is not a good one. Sorry, so x times x squared minus 9 square y second plus 2, well, let's do it here, x squared plus 2 sine x times x minus 3 y prime plus 3y equal to 0. Now let's solve the following. Let's see what are the regular singular point and the irregular singular points first. So I divide by the coefficient of y second. So you get y second plus 2 sine x over x squared times x minus 3 over x minus 3 times x plus 3 square y prime plus 3 over x squared x minus 3 x plus 3 square y equal to 0. So let's simplify. So this y second plus 2 sine x over x times 1 over x minus 3 times x plus 3 square y prime plus 3 over x squared x minus 3 square x plus 3 square y equal to 0. So what is p of x? So what are the this is my p of x, and this is my q of x. What are, this is x squared. So the bad points, the singular points, are x equal to 0, x equal to 3, and x equal to minus 3. So let's start with the smallest one. So for x equal minus 3, what is x plus 3 p of x? This will be 2 sine x over x squared times x plus 3. You will get 1 over x minus 3 times x plus 3. Now, is this analytic at x equal minus 3? Here I don't have a problem. Here I have x minus 3, and here I have x plus 3. This vanish at x equal minus 3. So this is not analytic at x equal minus 3. And this implies what? This implies that x equal minus 3 is an irregular singular point. It didn't pass the test on p of x, so I can stop here. It's not a regular singular point. Both p and q should be analytic. If one of them is not analytic, when you multiply it by x plus 3 for p and x plus 3 square for q, then it's not a regular singular point. It's a bad point. It's an irregular singular point. What about x equals 0? And now this is tricky. One of the reasons I did this example. And maybe a small review. So you'll get x p of x equal 2 sine x over x times 1 over x minus 3 times x plus 3 squared. Now here I don't have a problem at x equals 0. So notice that the limit as x goes to 0 of x p of x. Now see, this is going to 0. This is going to 0. So you don't know if this can be represented as a power series or not. But notice that if you let x goes to 0, this goes to 1 sine x over x by L'Hopital's rule. So this goes to 2 over minus 3 times 3 squared. So you deduce that 0 is not a bad point, really. So x p of x is analytic at x equal to 0. In fact, sine x over x is x cubed over 3 x minus x cubed over 3 factorial plus x5 over 5 factorial plus the whole thing over x, which is 1 minus x squared over 3 factorial plus x4 over 4 factorial plus. So it can be represented as a power series. So this is fine at x equal 0. Now what about x squared q of x? So x squared q of x is equal to 3 over x minus 3 squared times x plus 3 squared. Now this is analytic at x equal to 0. So it's valid for x, it's valid for p, valid for q, then x equals 0 is a regular singular point. Another example is x, the third one is x equals 3. What is x minus 3? P of x. This will be 2 sine x over x squared times 1 over x plus 3 squared. This is from here. And now this is analytic at x equals 3. And then x minus 3 square q of x. This will be equal 3 over x squared times x plus 3 squared. I'm multiplying q of x by x minus 3 squared, so simplify. And this is analytic at x equal to 3. And therefore what? Therefore x equals 3 is a regular singular point. And that's it, okay? So this is some example about regular singular point. Okay. Now I'll tell you, I will motivate the theorem. Okay, theorem. We are given, this is called Frobenius Fuchs theorem. I'm given an ODE y double prime plus p of x y prime plus q of x y equal to 0. Let x0 be a regular singular point. Then there exists at least one series solution of the form x minus x0 power r times, so this is y equal, times an analytic function. And now I told you why this, I suppose this to be true in the motivation video. So this is y equal x minus x0 power r summation from n equals 0 to infinity at x0 of Cn x minus x0 power n, or simply summation from n equals 0 to infinity Cn x minus x0 power n plus r. Okay. And the series converge for, now your r can be negative, okay? R can be anything. So the series converge for absolute value of x minus x0. It cannot be 0, so x cannot be x0 because it's a bad point. It's still a bad point. It's a singular point smaller than r, with r is at least the distance from x0 to the closest, well, to the nearest singular point. So if I have two singular points, then it will be, if I have many singular points and I choose one of them, there exists a series solution of this form and that converge for at least the distance from the singular point to the nearest other singular points. Okay. And now more, what is R? So if x minus x0, p of x equal p sub 0 plus p sub 1 x minus x0 plus p sub 2 x minus x0 square plus, and x minus x0 square q of x equal q sub 0 plus q sub 1 x minus x0 plus q sub 2 x minus x0 square plus. So I have the following power series representation because these two functions are analytic at x0. Then R, this is my R, I'm telling you there's at least one solution of this form, then R is a solution to the initial equation. It's called initial equation R minus 1 plus P sub 0 R plus Q sub 0 equal to 0. And the motivation of the proof, I already showed it to you, because I approximate the ODE by a Cauchy-Euler ODE, and this will be the auxiliary equation of the Cauchy-Euler ODE. I'm telling you there's at least one solution. This equation has two solutions. Yes, this is a second order. It either has one double root or two real root. But what I'm telling you, at least I will have one solution of the form x minus x0 power r times an analytic function. Okay? And where r solves this equation. Will I get two? For example, if I have two solutions to this equation, will I have two linearly independent solutions? Well, this is unfortunately not always true. And also sometimes this equation has one double root. How do I find the other one? Well, it's a second order ODE. If I can find only one solution, I can use a method of reduction of order to find the other solution. Now I'll tell you the full theorem. So our setup, let x0 be 0. Let's say this is regular singular point. It's good to know what is the initial equation, although when you are solving an ODE, you don't need it. When you are solving the ODE, the initial equation will appear. Okay, this will be in the next example. I will do 3 example video where you will see you don't have to find the index from the start. No, you will start solving the equation, and then the additional equation will appear anyway while solving. But it's good to have it if you just want to know the index. You are interested in the index, then you don't have to solve the equation. If you don't need the solution, you just need the important index, then this would be the initial equation. P sub 0 will be, you can say P sub 0 will be the limit as x goes to x0 of x minus x0 P of x. And Q sub 0 will be the limit as x goes to x0 of x minus x0 squared Q of x. This is how I find P sub 0 and Q sub 0. So if x0 is, so now the full theorem, x0 is a regular singular point to y double prime plus P of x y prime plus Q of x y equal to 0. And let's say I'm solving for x larger than 0. Okay. Now let R1, R2 be the roots of the initial equation. Okay. If R1, R2 are distinct and real, take R1 to be larger than R2. Okay. Now the theorem tells you there exists, this is called a Frobenius series of the form y1 equal x power r1 summation from n equals 0 to infinity cn x power n, which is summation from n equals 0 to infinity cn x power n plus r1. So at least I can find one solution using the larger index r1. Okay. And now the 3 cases. Case 1, if r1 minus r2 is not an integer, then a second solution that is linearly independent to y1 is y2 equal xr2 summation from n equals 0 to infinity d sub n x power n, and this equals summation from n equals 0 to infinity d sub n x power n plus r2. Okay, so if If the difference is not an integer, like let's say half and 1/4, 3 and half, then I have two solutions like I expect. I solve the initial equation, I get x power r1, x power r2 are the solution to the Cauchy-Euler approximation, then y1 and y2 that are x power r1 times analytic function, x power r2 times analytic function are linearly independent solution. I am done. Now case 2 is if r1 minus r2 is an integer, positive, okay, not zero. Then look at the following, okay, before motivating, look at the following. What if I have half and minus half, okay? Then I can have a solution that is x power half, or let's take easy example. Let's take 2 and 1. Then I can have a solution of the form x squared times 1 plus x cubed plus x squared plus. Or I can, and the second solution might be x power 1, and I do the same thing, and I might get x squared plus x squared. So you'll get, sorry. Okay, this is the first solution. Or the second solution would be x times x plus x squared plus x cubed plus. So it's x squared times the analytic function, x times the analytic function, but you see the result is the same, and I get two linearly independent functions. But in the case of the difference is not an integer, you get x power half power 1 plus x plus whatever, and let's say x power 1 times whatever is here, you will never get two linearly dependent solution because they will have a different, let's say, degree. Okay, this will have something powers of half, and this will have integer power. This will be integer plus half, this will be integer plus integer. So these two solutions that comes from initial root that whose difference is not an integer are always linearly independent. However, if the difference is an integer, you might risk get the same solution or two linearly dependent solution. So in this case, the first solution is the following. y2 will be equal c y1 log x plus summation from n equals 0 to infinity dn x power n, well, x power r2 times dn x power n, which is c y1 log x plus some n equals 0 to infinity dn x power n plus r2. Okay, so where c is a real number that can be 0. If it is 0, then I get two solutions. No, so notice if it's 0, if c is 0, then I get summation dn x power n plus r2, and I'm back to case 1. So as in case 1. So case 2 is somehow the worst case, okay? If the difference is not an integer, then I know that every index gives me a solution, if a linear independent solution. If the difference is an integer, I know that the larger index gives me a solution, but the smaller index might not give me a solution. I might not have a solution of this form. Then I will have another term that is y1 log x. Now case 3, if r1 equal r2, then in this case I only have one Frobenius series, then y2 will be y1 log x. So you see it's not c y1 log x, so it's never 0 here, plus summation from n equals 0 to infinity dn x power n plus r1. Okay. Now this is different, yes? But this is not as bad as case 2 because I know from the very beginning that I will have a log. Here I might have a log and I might not have a log in case 2. Okay? So in case 3, you find one solution using R1. To find the other solution, you will use the method of I will show you, it's pretty long, it's reduction of order. You will do reduction of order with series. This will be very long, very, very long, but I will do an example like this. Or you might get lucky, and when you do, for example, a power series solution near R, you might get a power series of a famous function, of an elementary function. For example, you might get x, you might get e to the x. You might get that this is not any power series, it's a power series of a function that I know, which means when I use reduction of order, it will be easier to use it on the function and not on the power series. But when R1 minus R2 is an integer, I expect one solution with x power R1, but the other solution might have a log x or might not have a log x. I should try. If I get another solution that is linearly independent to y1, then I'm good to go with R2. If I don't get, then I will have to use reduction of order. And you will see example as such, okay? There's a fourth case, which I will not. So this is the good, and the case 3 is the bad, and really case 2 is the ugly case, where I might get lucky, I might not get lucky. At least here I know my faith. What is my faith? I'm not lucky, okay? I already have a log x. Now, case 4, what if R1, R2 are complex number? Then R2 will be equal R1 bar. This is not included. I will not do examples this, but let's close the story. Then you will have complex solution which is y equals summation from n equals 0 to infinity Cn x power n plus R1. But here Cn are complex, so I will call it complex solution. Then y1 is the real part of yc, and y2 is imaginary part of yc. I look at the real part and at the imaginary part. Okay. And well, and you know that x power alpha plus beta I is equal to what? Is equal x power alpha x power e to the I beta log x. This is x power alpha cosine beta log x plus I sine beta log x. Okay. So I will stop. So you replace this by x power r, and now you have Cn complex, and you look for the real part and the imaginary part. This will give you two solutions. It's very long. We'll not do example with complex roots, complex index. We'll only do with real index. Okay. So in the next, so this is the theory, and then we'll do examples, because so far we do not know yet how to solve. We know that there exists solution. We'll do the theory and we'll see. You will see how it's solved. It's gonna be long examples. Each one of these is pretty long, especially that here you're dealing with 2 index. But you will learn it, and it's one method that you have to apply it everywhere.